Well, I think as I already talked, in environmental engineering part, your participation and also your personal is very, very important. Well, I'm not going to put any slides, any information for the environmental engineering part. So you really need to understand what I have taught during the environmental engineering class. This is very, very important. Okay. I think my PhD student gave a lecture how to design the batch reactor. You guys know the first time to design the batch reactor, you really need to understand what batch reactor is, and what is the application of the batch reactor. Think about the brewing of beer, and also think about the production of pharmaceutical products. They are very, very, good for the batch reactor items. And then you need to put the boundary condition and initial condition. The first time you need to set up the concentration of reactants, and then you want to know the concentration of the final products. Right? Well, you don't know the concentration of the final products, I mean pharmaceuticals, and the concentration of alcoholic beverage after brewing. That is very, very important. And then you need to set up the whole bunch of mass balance equation. That is very, very important thing. And the mass balance equation can be substituted by the rate expression. Well, you guys already know there are couples of different order of chemical kinetic reaction: first order, second order, third order, with respect to reactants. That is very, very important. So you guys can set up the rate equation and mass balance equation, and then you can have boundary and initial condition. Then mass balance equation is very simple. Well, the chemical compounds accumulated in the reactor equals the chemical reactants comes in, that is plus, and comes out minus. Because batch reactor, there is no coming in and coming out during the reaction. Those are usually zero. And then the chemical produced during the reaction, that could be plus. And then the chemical product that could be degraded during the reaction, that could be minus. You can put those two items using rate equation, and then what you want to do is, batch reaction usually related to the differential equation, and also those are whole rate reaction. Well, you even didn't want think about the steady state actually, but you just put it steady state if you want it. Well, anyway, and then what you can do is integrate each side, and then you can have a solution that is the time t concentration relation. So why the time and concentration is so important to design the batch reactor? Well, you may think about the as a civil and environmental engineer. Well, I really want to know the amount of cement and the amount of the reinforced steel. Is that right? Well, the design factor, as a design factor, the design factor you can have from the differential equation is concentration and time, is it? So how do you use those two factors for the design of the reactor? Even the pharmaceutical, reactor, or even the beer brewery reactor, how can you design that? If you know concentration and time, you can obtain the volume, right? So volume is very, very important for the design of the reactor. am I in the Alice in Wonderland? Okay, well, if you can understand what I'm talking right now, please check the video clip and run the batch reactor part. All right, and then I can expect my PhD student give you different type of reaction. Well, batch reactor direction could be zero order, and the reaction could be first order or even second order, right? Maybe if you really want to develop, chemical, pharmaceutical reactors, well, the reaction order could be 1.5 order, or with respect to X, or 1.6 order with respect to Y, or other factors. But we just want to deal with very simple, environmental reactor. So one contaminants and one reactor, and then we just put it A goes to B, and then we assume zero order and assume first order and second order. Second order case, it is very, very difficult to get the integration. So zero and first order. And then what you should do is direction is reversible or irreversible. Irreversible case is very, very easy, but reversible case, you need to consider another direction, right? So I really don't know. My PhD student gave you homework to design reactor, first order, and reversible reaction case. 너희들 내가 지금 무슨 말 하는지 알고 있네.
He gave one, he said if you want, you can solve anything. He gave.
Okay,
Yeah.
okay. Okay, she said he gave you the homework. Well, I think most of you already have advanced calculus. So using simple analytical solution, which is f prime plus q prime fc equals something constant. If you are using that equation, you can find it Shams series how to solve the that form. Well, we can easily get the solution, I think. That is very, very easy. So, think about that. If you know the concentration, initial concentration of reactant A, and if you know the reaction order, well, you definitely design the reactor. Batch reactor. First order, irreversible, reversible, and also zero case, which is very, very good. So that can give you concentration, time, and volume. So using those information, well, as a civil engineer, you can develop how much cement needed and how much length or steel is needed. Nobody wants to design those reactor using pre-stressed concrete. Have you ever had pre-stressed concrete press? No? Do you know what a pre-stressed concrete structure is? Michael knows that, right? Well, at bridge, long span bridge, well, it is very difficult to, construct that bridge on site. So the first time, you guys need to fabricate each section, and then, deliver it to the on site. And the important thing is you need to integrate those spans. So using the very thick cable, steel cable, and you can well, there is a little bit, this size of hole inside, and just put the cable and then put the stress. So these two fabricated section can be, strangled with this cable. We call it a pre-stressed, structure. Well, anyway, maybe I can give some more design how to develop the reinforced concrete structure for the rectors. All right. Today, I'd like to talk about the another type of rector called plug flow rector. What is plug flow? What is plug? Plug. Plug. Plug flow. What is the main assumption for the bench rector? Adita, do you know that? What is the bench rector? Basic, assumption on it. What is the definition of bench rector? Anybody? Carry on over there.
Assumption?
Yeah.
There is no flow behind.
Yeah. Well, that is very, very important thing. From the concept, bench rector, there's no concentration reactant concentration coming in. So Ca equals 0, and and then the bench rector actually completely mixed. So think about that. This is bench rector, and before starting the reaction, or let's say reaction goes to A to B. Let's say this is reversible reaction. So we just want to put some A here. So Ca0, at T equals 0, we know the concentration, right? And then we just want to give plenty of time to have good, products. So the rest, the time for start the reaction, let's say Ct, A, like that. So you guys know this concentration, and actually using the equation, you can estimate the concentration at time t. The important thing is you just have to put this reactant at first time, and then mix it, right? So using this impeller, at time t, the concentration A at any time t, at any spot, the concentration of this A is the same. So this is the basic assumption of the bench rector. So the concentration of A at any place at any time t equals 0, because this reactor is completely mixed. This is very, very important. But this is a very difficult, this is kind of very theoretical assumption. Think about that. If you have fluid mechanics, this site is actually dead zone, so you cannot easily get the good mixing this side. So, the stupid student or the student who doesn't have any interest in this study usually sit at last low or at the corner, because he wants to be, hidden, So I cannot, check it, right? So that is very similar case. This is that zone, so it cannot be easily, mixed up. But theoretically, we assume the concentration of A at any place are equal, right? This is what batch reactor is. But what is plug plug? Well, I don't have any. Let's say this is reactor. Yes, think about that. This is 500 milliliter pharmaceutical reactor, and I put some chemical here, and then I mix it, and mix it. This is actually batch reactor. Plug reactor is I am taking this one and walking through one direction. This is batch. This is plug reactor. Can you get that? So, when you design dam, or when you design some kind of water structure, in the river or lake, or any type of environmental structures in the river, in natural system, you usually assume the river flow as just plug flow. Well, actually, that is wrong. Right? You guys know that, right? The velocity across the river is totally different. This is a bird's eye view. Let's say, usually the river, this is a bird's eye view velocity profile. The velocity in the middle of the river is very fast, and this is, much smaller because there is friction here, right? And then what about the depth profile? It could be like this because friction, right? But when you guys design this type of water structure, you usually you assume all of the velocity are the same. And these depths are the same. This kind of concept is kind of 1970s or 1960s civil engineering, design concept. Why? Well, actually, they don't have any good, computation equipments to solve this chemical, to solve this, dynamic differential equations. Think about that. 1960s and 1970s, if you can solve one interesting differential equation, you can get a PhD. But nowadays, we have supercomputer, right? So we can actually set up the dynamic, differential equation. Well, although the equation include a very simple item, the mesh would be very, a big number. So you need to calculate using this equation using the supercomputer. Then you can actually consider the actual velocity of the river and with respect to depths nowadays. But the difference is not that much. We can save the money of come from the cement and reinforce the steel actually. And one interesting thing is this assumption is also wrong. So think about that. Is this Han River or Dachshund is the parallel? This is not right actually. It could be like this, and it could be like this. And also, this cannot be symmetric. So the actually velocity profile is totally different. But nowadays, the development of computer system, well, you can set up a differential equation, and the computer can give you the exact solution, actually. Then you can design. Wow, what a wonderful world. Right? But think about that. Who want to develop or design using supercomputer for the construction of wastewater treatment plant? Do you want that? Have you ever visited a wastewater treatment plant before? So do you think supercomputer system is needed for the designing of the... What about this? If you want to set up dam here, do you want to use supercomputer?
Maybe.
Maybe is around the 40% probability or 70%. What's your probability?
If the size of dam is big enough, I
Mhm.
think I have to use supercomputer to calculate the structure of dam.
Okay. And small computer, you don't want that. You just want to assume very simple assumption, and then, what do you think about this? If you just set up dam in the middle of the gapcheon, and if dam broken down, the water strike KAIST? Is it possible?
No,
No.
I think not.
Wow. Well, I think although gapcheon is very narrow and the water is not much, but if you set up dam, you can actually conserve the water, actually, million tons of water, actually. So you need to actually set up the bank each side. Why? Because water can be flooded, and it can be sunk down, actually, right? So a civil structure, you want to actually design those one very carefully. So you guys want to use supercomputer anyway. Maybe. What about the wastewater treatment plant? The wastewater treatment plant, if the direction Beijing struck by the some kind of earthquake or some natural disaster, does wastewater can kill the people? Yeah, maybe, right? Well, 1 year ago, when the tsunami actually struck the eastern side of Japan, Fukuoka, so there is some wastewater plant actually near the seashore. I can see the, fortunately, 100 years ago, very similar tsunami struck that area. They just set up a little bit natural, prevention bank along the coast. When the tsunami just strike, it is kind of a 30-meter water column just to push you. So wastewater treatment actually totally broken down. So the directors and the whole units actually broken. But at that time, the wastewater, the seawater is much more serious problem, not the wastewater. So compared to the natural disaster, or compared to the broken dam or the broken bridge, wastewater treatment plant, breakage is a little bit less, I think. So nobody want to use for computer actually. So important thing is, all days, think about that. The structures usually set up all days. Have you ever heard the old structure broken down due to the not good design? You never, maybe very small, cases, I think. Because at that time, they set up the assumption the first time. But that assumption can give structure much more stronger. So they are using more cement, and they are using more reinforced steel. So today, the reason why we want to use a supercomputer for constructing these dams and the civil structures is to save money. That is very, very important thing. So we don't have to put significant tons of zillions of amount of cement on them. Don't do that. Let's do it smart. That is nowadays civil engineers' idea. But the important thing, although the story is, although they have supercomputer results, they usually multiply the safety factor n. So they use the same amount of the cement and reinforced steel structure. Well, compared to the old days, the amount is much less, but they are still, don't below it. The real supercomputing results, they always multiply the safety factor actually. Well, anyway, so as I already thought, this is reactor and batch reactor completely mixed. If I am working through one direction, this is Prof reactor. Think about this. I think how to develop and solve the differential equation is very, very important. But I'm just asking you how the factors can be used for the real design of wastewater treatment plant or real design of the water dam. I'm not going to write that. All right. So think about this. User wastewater treatment plant, we put it as a WWTP. At first time, we'll say this is Michael's house, and he is doing making dinner, and after have nice meal, he just wash his dishes, and the wastewater actually go through the pipeline. And this is Adika's house, and there is Egan's house over there, Tom's house over there. So all of the wastewater are collected. Then it actually go through the wastewater plant. At first time, as I already taught, you guys want to take the water before gathering it. You want to screen the wastewater the first time because there is kind of very cold, suspended, solid here. You don't want to, and you don't want to allow those materials into the WWTP. And then, what you want to do is you want to first the celery. So here, the cold solid can be screened, and here, the smaller particle can be sunk down. Right? So we can collect the sludge and take it out. And this clean, relatively clean water can be overflowed. And here, this is, as I already taught, aerobic record. You can use it with the microorganism. So the microorganism, we call it as activated sludge. Activated sludge. Well, here, these are solids, right? And in this relatively clean wastewater includes carbon source and nitrogen source and phosphorus source. So the microorganism actually can eat this CNP. C could produce or CNP or TC. You guys know what BOD is, right? Biochemical oxygen demand and chemical oxygen demand. No, really. Michael, do you know what BOD is?
No, I forget.
You don't say kind of. You just speak it. What it is. Tom, idea?
No idea.
Anybody in here?
It's biodegradation. Or
Yeah. Well, I think you have one class. The important thing is, think about this. This is a potato chip. You just want to crush it into here and mix it well, and then using the microorganism here, just take it out a little amount of the microorganism and inject the microorganism inside here, and then stir it, mix it well, and give 5 days or any time for microorganism. Before starting the reaction, using DO meter, DO means dissolved oxygen. Well, I really don't know. Miso has that liquid. What is that? Is that the tea or kind of beer? So, let's say this is DO probe. DO is dissolved oxygen. So if you just put it in that coffee drink, you can measure the concentration of oxygen inside water. Well, you may think, most of you know, the water have much higher concentration of oxygen. That would be much healthier, right? You can say so, right? But it is depend on the concentration. If you take the maybe 40% of oxygen, well, your mouse actually the cell easily removed, and you can see the bones in your mouse actually. So the concentration is not there. Usually, we can from the tap water could be 2 ppm to 10 ppm. So this is tap water. Before starting the reaction, it could be, let's say, 10 ppm. And then put it, all things here, and mix it well, and give a 5 days for microorganism. Maybe microorganism can say, let me alone, for 5 days. So, and then, after 5 days, just to get rid of this reed, and then measure the DO again. Well, the DO of T equals 0 as 10 ppm, right? But after DO T equals 5 days, it could be 0.1 ppm. Why? This microorganism is aerobic bacteria. So this one actually needs oxygen to degrade this potato chip, crumbles, actually. So mix it very well, and then it actually degrades. So you can have the difference between these two. It could be 9.9 ppm, right? This is BOD. Well, as Michael said, we gave 5 days. This is BOD 5. Right? So BOD means the oxygen, the amount of oxygen that microorganisms want to use to function. That's great. again, BOD is the amount of oxygen which microorganisms need for the full degradation of carbon source. As I already talked, potato chip kernels. Got that? So BOD is the amount of oxygen which microorganisms needed. All right. So then think about it. Okay, can I start? So think about that. If this is just one piece of potato chip, or let's say if I just put the chicken fat, chicken oil, let's say 10 milliliter, or let's say some kind of very rotten egg, 10 gram. Well, depending on different compound can produce different oxygen. Usually, if the carbon source concentration are higher, well, microorganisms need more oxygen. So BOD actually increase. But think about that. Juntae actually want to have big lunch with his friend. Well, this is for granted, If he just take very simple lunch dish, he actually doesn't need much more oxygen actually. But he want to have a very nice bowl or 3 bowl of rice and bulgogi and any good meal. Well, definitely his body need more oxygen, right? So BOD actually is proportional to the amount of the calories to the amount of the carbon source or nitrous and phosphorus source. That is very easy, right? What is the COD? COD as well here, microorganism actually, what is it doing? I'm very sorry. What does it do in this reactor? Well, you can say degrading the potato chip crumbles. Can you refine this sentence with a little bit more scientifically? This is aerobic bacteria, right? So aerobic bacteria consume this potato chip crumbles. That means aerobic bacteria oxidize this potato chip crumble, right? So instead of this microorganism, if you're using oxidant, maybe you're using potassium dichromate. That is very good oxidant instead of the microorganism. You can measure COD. In this case, the amount of oxygen needed for the degradation of this crumbles, this is equivalent to the amount of potassium dichromate, 0.4 actually. Well, if you are adding more and more crumbles, you need to add more this oxidant, right? So the amount of oxygen can be calculated the equivalent amount of oxygen. So you can have COD. Right? 이해되니? 괜찮아?
네.
시험 문제 낼 거야 이거. 희건이는? 이해 안 돼? 그러니까 well, what about you guys? Tang, you understand what I'm talking?
Not really understand.
Michael?
Yeah.
Adhika?
Okay.
All right. Yeah, just to give this one in Korean because this is very very important concept. The first time, and I will give you another one in English. 그러니까 BOD 여러분 알겠죠 무슨 뜻인지? 그렇지? BOD 대신에 마이크로 오르가니즘 대신에 이 마이크로 오르가니즘을 갖다가 결국은 이걸 갖다가 이놈도 결국은 옥시던트이거든. 괜찮아. 우리가 우리도 밥을 먹는다는 뜻은 뭐냐면 이 밥을 갖다 먹고 밥을 옥시다이즈 시켜서 어떻게 칼로리를 갖다 얻어내는 거잖아. 그죠? 그러니까 세계사상 모든 이치가 리덕스 케미스트리인 거예요. 죽고 사는 것도 마찬가지. 리덕스 케미스트리고 내가 전자를 잃는다, 전자를 얻는다. 전자를 얻는다는 게 뭐냐면 내가 에너지를 얻어서 어떻게 살아간다는 뜻이거든. 그러니까 전자를 잃는다는 말은 내가 쭈글쭈글해진다, 늙는다, 죽는다. 그러니까 전자가 이제 바닥까지 가면은 어떻게 영원히 이제 하늘나라 간다. 응? 근데 이제 마이너스로 존재할 수 있습니까? Maybe it cost. 네. 그럼 여러분들이 확인하도록 보시고요. 근데 이제 이 미생물들 대신에 미생물들을 집어넣고 이제 오일 후에 디올을 갖다 잰 거잖아. 근데 이제 CO2 같은 경우는 이렇게 재니까 5일이 걸려. 와, 좀 5일 동안 그러니까 할 일도 많은데, 그렇지? 그래서 이놈들 대신에 그냥 케미칼을 갖다가 집어넣자. 그러니까 포타시움 다이크로메이트를 집어넣어서 여기 필요한 양만큼의 옥시전을 갖다가, 그러니까 사실은 여기서 이제 미생물들이 요 놈을 먹어가지고, 그지? 그러니까 먹으면서 필요한 옥시전의 양을 갖다가 잰 거잖아. 근데 결국 소모된 이 옥시전의 양이 여기에 들어있는 포테이토 칩 크럼블 양하고 어떻게 비교가 되는 거죠. 그래서 크럼블 양이 많아지면 미생물들이 더 많은 옥시전을 갖다 소모하기 때문에 BOD 값이 높아질 수밖에 없지. 그건 아까 이제 준태한테 얘기했듯이 준태가 그냥 조금 있다가 초코파이 하나 이제 먹고 전체로 때우는데 들어간 옥시전의 양이나 그리고 또 저 이제 뭐 불고기집 가가지고 이제 아버지가 오셔가지고 이제 준태야 많이 먹어라 그래가지고 이제 뭐 한 3인분을 갖다 때려 먹었다. 그때 드는 옥시전의 양은 틀릴 거 아니야, 그렇지? 그게 바로 BOD 차이인 거야, BOD. 그렇잖아, 소화시키려면 옥시전이 필요하니까, 그렇지? 마찬가지. 여기서도 이 컨테미넌트가 포테이토 칩이지만 이거 대신에 이제 정말 산업폐수에 쓰이는 그런 컨테미넌트라고 생각해봐요. 이 컨테미넌트의 농도가 높아지면 높아질수록 미생물들이 어떻게 더 많은 옥시전이 필요하겠지. 이놈을 갖다가 분해하려면. 그래서 BOD가 어떻게 보면 이게 좀 보면은 옥시전인데 이게 왜 이 컨테미넌트의 농도를 나타내요? 라고 얘기할 수 있는데 이거는 미생물들이 사용하는 그러니까 이 더러운 것들을 갖다가 이렇게 더러운 것들을 갖다 제거할 때 필요한 옥시전의 양인 거지. 그러니까 많이 사용하면 많을수록 옥시전의 양을 갖다가 더 많이 사용할 수밖에 없다는 겁니다. 근데 이 시간이 너무 기니까 우리 이러지 맙시다. 미생물도 잠깐 나와. 그 대신에 미생물 대신에 이 미생물을 갖다가 대신할 수 있는 이 포타시움 다이크로메이트나 중크롬산 칼륨, 이게 중크롬산 칼륨이죠. 그 다음에 이제 망간으로 된 놈을 갖다 사용을 해서 이 놈을 갖다가 그냥 밑에다가 이제 불을 때 이 프로세스를 갖다가 굉장히 빨리 만들어 버린 거야. 그래서 이제 이 놈을 갖다가 이 토탈리 그냥 지금 T=0에서 필요한 이제 옥시전의 양이 있겠고 T= 파이널에서 이제 필요한 옥시전의 양이 있는데 여기다가 이제 크롬의 양을 이 놈을 갖다 계속 이제 주입을 갖다 하는 거죠. 그래서 이놈이 완전히 이제 옥시다이즈 될 때 들어가는 크롬의 양을 갖다가 우리가 측정을 하게 되면 그 크롬의 양을 역환산을 해버리게 되면은 그때 소모가 된 O의 양을 갖다가 우리가 계산할 수가 있겠지. 그지? 그게 바로 스입니다. 오케이? 기철 이해돼?
네.
우리 케미스트리 쓰면 물론 뭐 다 알고 있겠지만, 그렇죠? But important thing is these are not the exact direct measurement, right? Well, important thing is we want to know what the enemy is. Think about that. Let's say your Gitcher's friend was dead, in the bed yesterday. So he want to know what the contaminants are, what the chemical compounds can kill him actually. In that case, you guys want to know the exact name of toxicant, right? But what do you think about that? Well, I don't know, but we measured the BOD in that body. It is very high. Well, let's say the chemical which kills teacher's friend. I'm very sorry, but just this is example. Let's say this is trichloroquinol. So very bad guy, just at 100 ppm of this TCP in the drink, and his friend actually take this. So as a CSI member, well, if I can say, well, his friend drink with 100 ppm TCP, well, that is very clear and very exact answer what he or what his parents want to hear, right? But if we don't have any analytical equipment to detect this chemical compound, if we have a very simple measurement equipment, just like dissolved oxygen, well, we can take this sample and put some microorganism, and we can actually have BOD, right? And also, we can do it in very short time with chemical COD. So at that time, I can say, as an SCI member, well, another CSI member, well, your friend actually was dead by 2000 ppm BOD, but we don't know the chemical name. Well, 1960s or 1970s, most of the environmental engineer and scientists are doing this one. They did it actually because they don't know how to detect this chemical. But nowadays, the development of the analytical equipment and the development of analytical chemistry, you can detect the contaminants, directly. That is very, very wonderful thing. So as a rate of TC, total carbon, well, here, the crumbles, the potato crumbles, we want to actually measure the direct concentration of total carbon of this potato chip crumbles. But nowadays, we can actually degrade this one, and we can investigate and detect the microchemical component of this, potato crumbles. Good days, actually. All right. Okay. And this is bioreactor, and then this is mixed, Ricker overall. Then it is going into the secondary settling, and here sludge actually collected and clean water. So compared to this one and this one, what's the difference? The microorganism actually eat up all carbon and nitrogen and phosphorus. The concentration of carbon, nitrogen, phosphorus is very low, right? So now it is the time to discharge. Well, here is the caption area, and then you can discharge this one directly. But nobody wants to do this, right? Because some of you may be very wondering, what if this this microorganism can, contaminate our ecosystem? So what the people usually doing is, you just put one more process here, which kills microorganisms. We call it disinfection, using chlorine and any other, oxidant. So, well, actually, humankind actually using and exploit the microorganism. Very poor. wicked human being. And discharging, you know. So we are actually designing this reactor. So previous class, my PhD student taught you how to design this aerobic basin with microorganism. So this is, let's say this is just a batch reactor. So this is very big basin, just like this size of the basin, you know, and filled with the microorganism. Let's say 2.2 meter. And then as I went up, this is batch reactor. So what is the basic, you know, assumption of the batch reactor? The concentration of any spot, any contaminant, any spot at any time should be equal, right? So how do you want to mix it? Well, you can easily put the deep impeller, right? So if you want to well mix the water here, how big impeller is needed? Wow, that should be just like this big size of the impeller, right? But the important thing is if you use one impeller, you never ever have good mixing. Well, there are very, you know, dead zone around here. So how can you overcome this problem? And also, microorganisms need oxygen. Well, can you see the you know, golden, you know, fish in the you know, small reservoir in your house? What do you do usually? Yes. So you just put your paste into the water and doing the bubbling with your mouth. Wow, he is very, very, you know, fish admirer. Okay, what do you do? You need to have a bubbling system, right? So just set up some bubbling system here. We call it air diffuser. So diffusing air here, it is just like the, you know, just air mixed up the liquid. You know. So you can have comparatively well-mixed reaction zone here. Or you can put some mechanical agitator. Agitating. So put it agitating. So this is kind of pedal on the surface. It is just like this. So it can agitate water. So water actually jump up and going down, and it can entrap oxygen, air, into the water. So you can have mixing, and you can have actually air. So you can have the you know, this reactor actually. So this is a use of batch reactor. But what is the proper reactor? Well, batch reactor is just a batch reactor, right? The proper reactor is continuous reactor. So as I already talked, this is bird eye view. Let's say, as I already talked, this is just a batch reactor. Batch reactor is marching in, like this. So why we want to use proper reactor? And also this is continuous, right? I think we already. 프로포 리액터가 쓴 이유가 있겠죠, 그죠? 만약에 프로포 리액터가 좋지 않으면 왜 뒤에 나올까? 그러니까 물론 이제 우리 조선말은 이렇게 그러니까 이 끝말이 중요하다. 이렇게 옛날에 누가 살았는데 뭐 어떻게 하다가 마지막에 그냥 이렇게 한 칼에 죽었습니다. 뭐 이런 게 그러니까 이 끝말이 가장 중요하거든. 그러니까 프로포 리액터를 많이 사용해요. 프로폴 리액터, 그러니까 이제 케미컬 리액션이 이 지오메트리, 그러니까 지오메트리적인 건 우리가 배치 벡터를 갖다 사용하다 하는 거하고 이 길쭉하게 해가지고 이제 컨티니어스를 이제 만드는 거하고 이 지오메트리를 틀리게 디자인을 함으로써 케미컬 리액션을 더 빠르게 만들어. 그러니까 더 짧은 시간 내에 미생물들이 어떻게 이 그러니까 카본 소스라든지 MP 소스를 갖다가 그러니까 섭취할 수 있도록. 그래서 예전에 1960년대, 70년대 리액터, 그러니까 WWTP에서는 모든 게 다 이런 리액터였습니다. 그냥 큰 이런 베이진에, 그치? 이거 한 4배 되는 베이진 사이즈 깊이 한 3배 정도 되는 데다가 이 미생물을 액티베이트 슬러시 때려놓고 모든 입질에서 나오는 하수 모아서 처리를 했어요. 근데 이제 이걸 지오메트리를 조금 틀리게 이렇게 해서 계속 길게 이렇게 사실 리액터가 어떤 이 bird's eye view 알죠? 이렇게 쳐다보는 거. 이 bird's eye view로 해서 이렇게 이런 리액터를 갖다가 우리가 어떻게 이제 바꾸냐면 엔트런스를 여기가 만들어서 이런 식으로 물이 돌아가도록 만드는 거죠. 이렇게. 그러니까 돌아가도록 만드니까 각각 이제 요 놈 자체들이 이제 배치 리액터가 이제 딱딱딱딱 하게 되는데 그 놈이 이피션스가 더 좋더라는 거죠. 그러니까 그래서 왜 좋은지는 그러니까 그 디퍼런셜 이퀘이션 그러니까 수학적으로 다음 시간에 증명을 하도록 하겠습니다. And question. I'm very sorry about the final part which was spoken in Korean, but I will explain it later next time, which is not that important. Very important.